Hello all, welcome back to this online recording sessions in deep learning concept from data science concepts. Okay, so in this lecture we are going to see what is bias, what is variance, what is trade-off. Okay, so how these cases will be coming in overfitting and underfitting problems. Okay, so let us see one by one what exactly they mean. So how to overcome, what are the different techniques that can be used to overcome overfitting and underfitting. Okay, after discussing what is bias, variance and trade-off. Yeah, so what is bias, variance, trade-off? Okay, bias, variance, trade-off in machine learning involves managing of two types of errors. Okay, in machine learning this can be related to deep learning also. Here also will be coming two types of errors, overfitting and underfitting. It generally occurs. Okay, so why this occurs? Yeah, let me give a scenario. Okay, so we are designing a neural architecture, right? So if our neural architecture is very simple, okay, we may think that if I take less neurons, there is a less chance of complexity, so I can get the output easily. Okay, so that is not the case here. Okay, so if the neuron is very simple, that exact information may not be captured properly and the models may not be built properly. Okay, so that is what we be coming the phase. If the model is very simple, okay, if the model is very simple, if our architecture is designed with very simple, okay, then we may face problem. Okay, if our architecture is very big also, okay, if we design very complex architecture, okay, again there is a problem. Okay, by designing very complex architecture, everything becomes complex. Okay, so the information cannot be passed properly and the output is also may take many steps. Okay, it involves many steps to extract that information, okay, from complex architecture. Okay, it shouldn't not be simple or complex. Okay, simple and complex problems will be coming. The architecture should not be very simple, it shouldn't be very complex. Yeah, so what is bias? So bias arises from simplistic models. Okay, so bias arises if the model is very simple. Okay, variance results from complex models. Okay, so variance arises for complex models. If the model is very big, okay, in that case variance problem will be occurring. Okay, if the model is very too simple, then bias problem will be there. Okay, so this is nothing but a underfitting. So this is nothing but a high bias, means it is nothing but a underfitting, and the case is that the model is very simple. Okay, simple architecture. Okay, so high variance. Okay, high variance means we can say it is overfitting. Overfitting. Okay, so overfitting means whenever I say it is overfitting, I mean it is having high variance. Okay, high variance, and the model is also built with complex, okay, complex neurons, and the entire architecture is very complex. Okay, many layers are involved in it. Okay, so that's why if the architecture is very complex, we are getting overfitting. If the architecture is very simple, we are getting underfitting. Okay, so how do we balance this? Okay, how do we balance this error? Okay, it shouldn't be neither too complex, it shouldn't be neither too simple. Okay, how do we balance? Okay, so balancing this error is crucial for creating a model such that the data is fitted well and the model is built very well. Okay, yeah, so bias. So bias, as I mentioned, okay, bias means the model is very simple. That means high bias, it is arised in underfitting. The case we call it as underfitting. Okay, so bias refers to the error due to simplistic assumptions, okay, in the learning algorithm. Okay, a model with high bias tends to underfit the data. Okay, a model is having high bias means it is indirectly it is a prone to underfitting. Okay, meaning it oversimplifies the underlying patterns. So all the patterns are getting very simplified. Okay, we may think this is a shortcut. Okay, this is a very shortcut to extract the output, but indirectly we will be missing the many outputs. Okay, so while training also you see using GPUs. Okay, so why do you use GPUs while training the deep learning concepts? Okay, in order to make the training very faster, right? So we are choosing the shortest route. Okay, we are making the architecture very simple so that it gets trained faster. Okay, so what is the drawback of this? What is the drawback if you do like this? Okay, so we'll be missing the information. Okay, some underlying deep information can be missed out. Okay, some patterns, hidden patterns may be missed out. Okay, yeah, if the training leads to poor prediction performance, so which indirectly leads to a poor performance. Okay, since the complexity of the information cannot be captured because the architecture is too simple, that is, it is not capable of handling more information and the exact information. So example of high bias. So you can take real life example of high bias. Okay, say suppose if you are trying to predict using linear regression algorithm, so what you're trying to predict? House prices. Okay, so if you're trying to predict the house price, okay, using linear regression model. Okay, based on what? Number of square footage. Okay, if the square feet are more, then it depending upon that the cost is finalized. Okay, so indirectly if you predict like this, if you consider two parameters, what is the case if there are no bedrooms or if there are no kitchen rooms or if there are no properly designed housings? Okay, so in that case the model linear regression fails, right? So even though we are trying to purchase the house which is having more square yards, even though we are purchasing more which is having more square yards, we are not having the all the segregated rooms. Okay, that means we are not having the proper bedrooms, proper kitchen rooms, proper halls. Okay, area is more, but the parts, okay, the what we are expecting when we are trying to purchase a house with a good price, okay, we expect all the partitions, right, with good ventilations and all. Okay, that is what here. Okay, that's the what problem that we may overcome if we take make our model very simple with less parameters. Okay, while predicting. Okay, next, variance. Okay, if we design with very complex architecture. Okay, so here also you can take the real life example. So handwritten digit recognition. Okay, so imagine training a decision tree with very deep structure on a data set of handwritten digits. While the tree can fit the training data perfectly, it might perform poorly on new. Okay, so unseen digits also. So there may be transparent digits also. So there may be unseen digits also. In that case, what it has, which has essentially memorized. Okay, so during that it performs badly. Okay, so on the whole, this is an example. Okay, so what is variance? So variance, on the other hand, it's the error due to excessive complexity. Okay, as I mentioned, if the architecture is very complex, then we can say it is having high variance, nothing but a overfitting. Okay, yeah. So let us see this total error when we are calculating total error by calculating total bias and variance. Okay, so we will be taking bias square plus variance. Okay, so we'll be taking this in order to calculate total error. Okay, bias square plus variance. Okay, yeah. So identifying underfitting and overfitting. Okay, so we can understand bias and variance. Okay, so let us discuss. Okay, let us discuss this. Okay, what is underfitting? So underfitting occurs when a model is simplistic. Okay, you can see here. Okay, when training test and testing set. Okay, so in training set, what we are trying to do, a model with high bias will struggle to fit the training data. Okay, so the model will struggle to fit the training data properly. Okay, it will not get proper neurons to fit this data to that neurons. Okay, so if there are good neurons, comfortable neurons, this information can be passed on to those neurons, then we can get good information, good outputs, right? So in that way, the training set data cannot be fit to exactly. Okay, cannot be utilized properly. Okay, cannot be set properly. Okay, so summary. Okay, underfitting results in a model that fails a grasp. Okay, so proper training test split up will be the disturbance. Okay, if there is an underfitting problem. Next, overfitting. So overfitting happens when a model is excessively complex. Okay, as I mentioned. Okay, so capturing not just the patterns. So if the complex, if the architecture is very, very complex, very big architecture, okay, so the information is very small. So in that case, what happens, these big neurons will capture noise also sometimes. So extra other information also will be captured like noise, so resulting wrong result. So wrong results will be predicted, okay, by capturing the noise. Okay, so this case is called overfitting. Okay, since we have more complex architecture, we take a grant to pass more information even though we are having small data. Okay, yeah, you can see here, okay, how the training set and test set will be considered. Okay, what happens to the training set and test set if we are having the overfitting case. Okay, yeah, so this is the graph. Okay, so if the graph is like this, okay, from here to here we say it has underfitting, that means high bias. So this is overfitting. So the region between underfitting and overfitting is called the best. Okay, so the best region, okay, is between underfitting and overfitting. Okay, that is what you can see here. Okay, trade-off, this is called trade-off. Okay, so this is variance, this is bias, okay, this is general error. Okay, so you can see in between we are getting the general error, okay, which is best accuracy. Okay, so here you are having overfitting, here you are having underfitting. Okay, in graph we can visualize it. Okay, so you can see individually also how the overfitting graphs separately looks, how the underfitting model looks, so how the best accuracy model looks. Okay, graph. Okay, yeah, so validation error curve, that is what the validation error curve, this is what validation error curve. Okay, so it is describing bias underfitting region on the left side of the curve, a region associated with high bias or underfitting. Okay, so in this area the model complexity is too low. Okay, yeah, next we have variance overfitting on the right side. Okay, so entire region is associated with the high variance or overfitting. Here model complexity is excessively high. Okay, so what we need to do in order to overcome this overfitting and underfitting? Okay, we need to have some, okay, some techniques in order to overcome overfitting. Okay, so mainly overfitting we have many techniques. Okay, so let us see. So after this, let us see for this bias variance trade-off. Okay, so bias means underfitting, variance means overfitting. Okay, so what are the solutions to be addressed? Bias variance. Okay, so to strike the right balance with and address bias variance issue, consider the following solutions. Okay, regularizations, we have regularizations like L1 and L2 regularizations. Okay, next feature engineering. Okay, so proper cleaning of the data, so removal of noise also can be removed in the feature engineering. Okay, next cross validation, so we have different cross validations, k-fold cross validation, so stratified cross validation. Okay, so we have different cross validations. Okay, so where we need to use cross validations, how we need to split the data. Okay, so into training and testing samples, how we need to split using cross validation techniques. Okay, in order to get proper information by overcoming overfitting and underfitting. Okay, by using ensemble methods also like random forest and gradient boosting. Okay, so we combine multiple models to achieve better performance also. So we can combine multiple ensemble models like random forest and gradient boosting also in order to address this bias variance trade-off. Okay, so we can collect more data. Okay, this can be helpful for simple architecture. Okay, if the data is very simple, in that case collecting more data helps to overcome this problem. Okay, with the proper good information, even though the data is simple also, but since we are having good patterns, good data, it can be considered sometimes. Okay, so collecting more data also sometimes helps us to overcome and address this bias variance. Okay, yeah, so next we will see the how to overcome the overfitting. Okay, so there are different various techniques to overcome the overfitting. Okay, so let us see one by one how does this overfitting. Okay, so out of all the techniques that we will be discussing here, dropout layers and regularizations are to be considered more, okay, which has given priority more in order to come overfitting. Okay, so yeah, so as we have seen overfitting, okay, yeah, these are the different techniques that can be used to overcome overfitting. So in order to overcome overfitting, okay, we can use simplifying the model, we can use early stopping, we can use data augmentation, we can use regularization, we can use dropouts. Okay, these are the techniques to overcome overfitting. Okay, okay, yeah. Next we'll be elaborating separately what is the simplifying the model. Okay, so simplifying the model means when dealing with overfitting is to decrease the complexity of the model. Okay, so overfitting means the model is very complex, right? So in order to reduce that complexity, what we will do, so we need to simply remove layers or reduce the number of neurons to make the network simple. Okay, so we can remove layers or we can remove neurons also to make the architecture very simple in order to overcome overfitting. Okay, so this is one technique to overcome overfitting. Okay, so while doing this, it is important to calculate the input and output dimensions also of various layers involved in neural network. Okay, yeah. Next, early stopping. So early stopping, what in simple network we are deleting the neurons. Okay, so what we are trying to do, we are trying to remove the layers and reduce the number of neurons. Okay, simplifying the model. Okay, so this is another technique to overcome overfitting. Okay, early stopping. Okay, since all neurons learn exclusively by using gradient descent, early stopping is a technique applicable to all the problems. Okay, this method updates the models so as to make it better fit the training data. Okay, so up to point. Okay, so up to some point, so we'll be stopping it. Okay, this improves the model's performance on data on test set. Okay, so if you stop at a particular point, that will be a better approach, I can say. Okay, okay, improving the model's fit to the training data. Okay, early stopping rules provide guidance as how many iterations can be run before the model begins to overfit. Okay, so how many iterations? Okay, I cannot run many iterations in order to get overfitting. Instead that I can use put a constant on the number of iterations and then I can train the model. Okay, that means early stopping. So at what iteration I need to stop. Okay, next, data augmentation. So using data augmentation, how you can simplify the architecture from complex. See, so same data, instead of taking 100 samples, I may take 10 samples only and I can augment the data. Okay, so augmenting the data in the sense, so this is the original image. So if I augment it, you see, so the dog is looking straight. So here in the original image, the dog is looking sideways. So if I augment it by tilting the angle, so the dog looks straight here. Okay, so in the next case, you can see the dog is looking the other opposite side. Okay, so here the dog is putting tail backwards. Okay, so this is what the same image I'm trying to augment it by applying different parameters. Okay, so I can take angle. Okay, I can change the angle of this image, so I can increase brightness of the same image. Okay, so I can apply some parameters, okay, in order to augment the same image. Okay, in order to create the multiple images of the same kind. Okay, see, so the dog is observed from the different angle. Okay, you see this dog. Okay, it is visualized from the right camera. Okay, so in this way, the original image only we are generating different images. So that is nothing but a data augmentation. Okay, so in this way data augmentation, okay, some samples can be augmented in order to avoid many samples. Okay, so here you can see, okay, increasing the size of the data, okay, is a very complex thing that we are overcoming here by taking only few samples and augmenting it. Okay. Next, regularization. Okay. So here regularization means why we are applying regularization generally? In order to reduce the complexity, right? So it is done by adding a penalty to term the loss function. Okay, there are different regularization function. Okay, so we need to study different regularization function also in order to avoid overfitting. Okay, when to use L1 regularization, when to use L2 regularization in order to overfitting. Okay, so the most common techniques are L1 and L2. Generally there are many regularization techniques also. So L1 aims to minimize the absolute values. Okay, L1 is considering minimum absolute values. Okay, if you see here. So L2 is squaring up. Okay, L2 is squaring up. Okay, squaring up the here. Okay, here you see L2 penalty aims to minimize the squared magnitude of the weights. Okay, so here you see this regularization we need to be having enough knowledge whether to apply L1 regularization or L2 regularization. Okay, you can see the difference between L1 and L2 regularization. So L1 will do sum of absolute values weights, it will do absolute values, whereas L2 will sum up squares. Okay, it will do squares. Okay, squares means what? Indirectly it is increasing the memory size. Squaring means what? 2 square means 4. So 4 is a large value, right? 5 square. 5 square is, if you are squaring the values, what is happening? The memory size is also getting increased, right? So in that way you can see here what is the drawback of L2. Okay, so when to use L2? Is it the necessary situation to use L2 regularization, or is it the necessary situation to use L1 regularization? Also we need to be known. Okay, so L1 generate models that is simple and interpretable because it is involving absolute values. Okay, so here L2 regularization is complex data patterns because squaring up. Okay, if there is a complex pattern also, it is getting squared up means it becomes more complex. Okay, so 12 square, it is 144, it is again becoming very complex, 3 digit. Okay, yeah, so in that way L2 regularization or L1 regularization, we should be having enough knowledge. Okay, so L1 is the robust to outliers, L2 is not robust to outliers. Okay, so which techniques better to avoid overfitting? Okay, so the answer depends upon the situation. Again it depends upon the data sets that we are taking, the problematic approach that we are trying to solve. Okay, so L1 is better if the data is simple enough to be modeled. Okay, if the data is very simple to be modeled, then we can use L1. So for most of the computer vision problems, L2 regularization almost always gives better results. Okay, so generally for computer vision problems we will use L2 regularization, which gives better results. Okay, so whereas L1 has added advantage of the robust outliers. Okay, so the correct choice of the regulation depends upon the problem. As I mentioned, it depends upon the problematic approach, it depends upon the what kind of problem we are trying to solve, how the data is actually. Okay, yeah, so next technique is the dropout. See, in dropout what you are trying to do, this is the complex architecture, right? This is the complex architecture which is having these neurons, these are layers. Okay, in these layers we are having all the neurons. Okay, if you observe, what you are trying to do, we are trying to remove weak neurons. Okay, that means indirectly we are reducing the complexity. Okay, if you reduce the complexity, overfitting problem can be overcome, right? So I am removing the weak neurons or neurons which having less information that are not necessary for our problem. Okay, so in that case you can remove those neurons. Okay, so I am removing it, which the neurons having less information that may not be useful for our model building. Okay, so dropout on the other hand modifies the network. Okay, so see, L1 and L2 reduce the overfitting by modifying the cost function. So L1 L2 will modify the cost function, but dropout will modify the network. Okay, so there we are modifying the cost function or loss function or error function with the help of L1 and L2, but here we are trying to modify the architecture. Okay, so randomly dropping the neurons from neural network during training in each iteration. Okay, so when we drop different sets of neurons, it's equivalent to training different neural network. Okay, yeah, so we should also be conscious. Okay, until and unless it is the necessary situation, we shouldn't remove. Okay, so that may be also somewhat drawback. It may lead to underfitting also. If you use dropouts, okay, more dropouts, it may lead to underfitting also, because sometimes the model may become too small also if you remove neurons. Okay, so you should be again select which technique is better out of all the 5 techniques that we have discussed for overfitting. Okay, so that's it for this session. I hope you learned a few techniques in order to overcome the problems like overfitting and underfitting. Okay, these techniques will help you out. Okay, so thank you all. So thank you for giving up this opportunity. So thank you all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.